So we're now going to look at an example of how to find roots of a complex number. And we're going to start with a kind of a weird example, because we're going to start with a complex number 1. And we're going to compute its fourth roots. So how to do this? Well, it turns out that the key is to express this complex number in as many different ways as we can. So, well, 1 can be expressed as e to the I 0, e to the I 2 pi, e to the I 4 pi, and let's even do e to the I 6 pi. So we could continue like this forever. So basically here I have the unit circle in the complex plane. And then I say that, well, the point 1 is here. That's e to the I 0. And then if I go a full circle here, e to the I 2 pi, another full circle, e to the I 4 pi, and so forth. So all of these numbers are the same, just different representations of the same number. So why do we care? Well, we can now divide this angle by 4 in each instance. So here, for instance, well, 0 divided by 4 is just 0. I can write it like e to the I 0 still. Here I get e to the I 2 pi divided by 4. So if I compute this, it's e to the I pi half. And here I get e to the I 4 pi divided by 4. This is e to the I pi. And here I get e to the I 6 pi divided by 4. And here it's e to the I 3 pi divided by 3 pi divided by 2. And let's even do one more here, 8 pi. And then I get here e to the I, so I'm dividing the angle by 4. So I get here e to the I 2 pi. Now, of course, all of these numbers were the same. But when I divided the angle by 4 in each instance, I'm getting numbers here that are different. So this is a different number than this. So we can see it down here most clearly, perhaps. So here, so let's give them names. So let's call it C0, C1, C2, C3, C4, and I could continue like this forever, C5, C6. So what do I get here? So here I get e to the I not as before, and then e to the I pi half, well, he's here. And then e to the I pi is here, e to the 3 pi halves is here, and then here e to the 2 pi, well, we're back here again. So each time I jump by 90 degrees like this. And of course, after having done the 4 first jumps, I'm just going to repeat my roots here. Well, what's the point of this? Well, the point is now we've found all the fourth roots, because here if I take the 4th power, this becomes that. And here if I take the 4th power, this becomes that. And here when I take the 4th power, this becomes that. And here when I take the 4th power, this guy becomes that guy, and so forth. And also he becomes him when I do the 4th power. All of these are the same guy, namely 1. So these guys here are the 4 different fourth powers of 1. So a natural question now is, have I found all 4th powers? Yes, I have. This actually follows from the fundamental theorem of algebra. So so what does it mean? So x is 4th power, or 4th root. Sorry if I said 4th power a couple of times. 4th root of 1, if and only if it solves x to the 4 is equal to 1. This thing here is if and only if x to the 4 minus 1 is 0. That is, x is a root of this 4th degree polynomial. And by the fundamental theorem of algebra, we know that this guy has at most 4 different roots. And up here, these 4 guys are all different roots of this polynomial here. Hence, these are all roots of this polynomial here. So we have indeed found every single 4th root of 1. Finally, what if I'm to find 4th roots of a more general number. So let's say this guy here. Well, the trick is the same. So I now express him in as many different ways as I can. So like this, and so forth. And now I can just repeat the things. I'm taking the fourth roots here. So first of all, I'm dividing the angle by 4. And then I'm taking this, the modulus, so this is a positive real number. I'm taking his proper fourth root like this. And here I have a complex number who, when I take the fourth power, becomes this. And I can do the same here. So r to the quarter, then ei theta divided by 4 plus 2 pi I divided by 4. And if I take the fourth power of this, I get this back, and he's the same as him, who is z. And so on and so forth. Here I take the fourth power like this, and then I'm getting here this thing. And again, every conceivable fourth root of z has to satisfy x to the 4 is equal to z, which is the same as satisfying x to the 4 minus c equal to 0. And this is just a constant. And again, so the fundamental theorem of algebra, he doesn't care if you're real or complex or whatever. He says that this has at most 4 different solutions. And if you continue this way, you'll find exactly 4 unique solutions. So we're done.